Alright guys, so we have a midterm next on Thursday, next lecture. So I'm not gonna be here, so my graduate research assistant is gonna be here. So he took this class last year, but the exam is clear, and I believe everything will be set up for the exam on Thursday. Does anybody have any questions? The exam, just a few things. The exam is gonna start at 9:30 sharp, and is gonna end at 10:45. You are allowed to have a cheat sheet, like you have one page you can write on the back or in the front or both, and you're allowed to bring. Have you guys were able to locate the integration table in the textbook?
Oh,
Right.
like
So how
the
did
one.
you do the homework?
Well, we use your. I
Has
use
the
your.
triangles?
I use
The
your.
one
like-
the one I have. All right. So in the textbook, in the syllabus, there's a textbook. It's called the Fundamentals of Structure Analysis, or Structure Analysis Fundamentals. You will find this in the second table in the appendix. It's table 2 or something. So you can print it. I printed 10 pages just for you. If somebody forget it, but it's better you come with your own like chain with you. Okay? So this is the only 2 things that you're allowed to come with in the exam. And you are not allowed to write on the back of the page that has the integration table. Only the one page that you have. That's it. Okay? Does anybody have any questions so far? Alright. The exam is 4 questions, as I said. One is going to be on the static determinacy and indeterminacy. Another one is going to be on arches and cables. Another one is going to be on conjugate beams and double integration method. And another one on the virtual work. So 4 questions. Each question is 25 points. So try to divide your time equally between the questions. All right. I got some questions after the class last week. Some of you were asking, yeah. So like we solved this beam last time using the virtual work method. Like we had a beam like this, and this beam has a load W, length L, and I was asking what is the deflection that we are gonna have in the middle using the method of virtual work. Do you guys remember the steps how to solve a problem like this? What are the steps? First you get reactions, and then get the bending moment for the original beam. And then the second, remove the original load and put a unit load at the point that I'm asking you to get the deflection at. If I'm asking at the middle, you put unit load in the middle. If I'm asking here, you put unit load here. So if at the middle, so you are gonna put something, you remove all the loads and you load Q equal to 1 here, right? But what if I have the same same problem, but with load W and also load B in the middle? What would you do? Alright, you can do the same thing. You will find the reactions from both the loads, and then you will get the bending moment for both loads, and then you remove the loads and put unit loads. Same thing, but the thing is, our tables is not equipped for both of them together, but you can take this and divide it into 2 problems. Like you can make this, get the bending moment from this plus the bending moment that comes from this one. This one is gonna give you moment positive. This moment is positive, and here is WL squared over 8, right? And this one is gonna give you triangles like this, and the moment here is gonna be equal to BL over 4. Then you integrate both with this when you put Q equal to 1. Q equal to 1 is gonna give you BL over 4, and B is equal to 1. So 1L over 4, that's the moment. So it is gonna be the summation of integrating this with this and this with this. So you are gonna have, if you remember the integration M1, M3, DL, is gonna be integration that has a piece and another piece, 1 and 2. One is coming from this and one is coming from this, right? We got that? Because it is the we call it the method of superposition. It's like you solve this problem with the original load W, and then you solve the with the original load B. Okay, so this is how you do it. So you will go to your figure. Yeah. You will go here. I have the parabola, and then I have this triangle. So this with this is gonna give you 1/3, m1, m3, and there is a rest of the equation. And then you integrate this triangle with this triangle, and then you will come here and do the integration. All right. Try to do this at home. Solve the same problem and put unit load and put load B, whatever it is, and try to solve the same problem. Okay. All right, so that's one question I got last time after the class, and also another question, I don't recall. But yeah, so this is how to solve this one. All right, does anybody have any question? Are you guys all ready for the midterm?
If I get a moment diagram that is not perfect like that one, like the parabola is not perfect, but it's maybe more.
It's gonna be parabolic, but the thing is, if I'm gonna draw the bending moment directly of this two, so you are gonna have, this is the beam, you are gonna have here, the moment, the bending moment in the middle is gonna be equal to WL squared over 8 plus BL over 4, okay?
No, but
And then you are gonna stretch a line here, and then the parabola is gonna be something like this, and the drop in the middle is gonna be equal to WL squared over 8.
But I mean, what if the load is not in the middle? So a little bit shifted. The moment diagram now is not going to be a parabola symmetric like that.
There's also an equation for that here, because the thing is, yeah, like if you are saying like if it's here,
Yeah.
same thing. You are gonna try to find the bending moment here, and then you are gonna draw a line here and draw a line here, and the parabola is gonna be something like this and something like this. And by the way, when I say here the W L squared over 8, it's this part. Okay, same thing here. You are gonna have a parabolic curve here and a parabolic curve here. That's the final bending moment.
Which one do you use from the table to do that?
You are gonna find here actually the triangle that we have here. Yeah. Look, the triangle that we have here is not symmetric. It's A and B. It can be at any position.
Well, but our moment is not a triangle, or is
But
it?
if you made a superposition, you are gonna have, rather than having W is gonna be the same, this one, and B rather than being here is gonna be here, and it's gonna be something like this. So you are gonna integrate this triangle with this triangle.
Oh, okay. Okay.
And then you are going to integrate this with this. So B is not going to impact W because W is uniform on the load, on the beam. Okay? All right. So the way that triangle that is here, it's a general. So you have A and B is a general at any distance. If it's in the middle, so A is equal to L over 2 and B is equal to L over 2. But if it's not, you will try to find what is A and what is B. Okay? All right, so that's all for now. We are all ready for the midterm?
No.
Está bueno? كله تمام? Everything's good? That's Arabic, sorry.
What does
So,
that mean? Also
Está
ready?
bueno. Everything's good. Yeah.
It's a question about the homework. So I was doing one of the problems, and I realized that I got the answer right when I didn't include the first boundary condition. So there's sometimes that we have to include the first and the second boundary condition. Honestly, I didn't understand why. I asked ChatGPT. I got more confused. So can you please?
Oh, so what is the question? Like, tell me what's the
So
problem?
for example, we have the cantilever beam.
Is it conjugate beam, virtual load?
Double integration method.
Double integration method?
Yeah.
So what was the problem?
It was just like the first problem. It was a cantilever beam,
Mhm.
distributed load, and
Like this,
Yeah.
Yeah.
Distributed load.
and then
Find the deflection.
W,
Yeah,
that's it.
yeah,
And there's L.
yes,
And you want to find it by double integration.
yes.
Okay. So with this problem, best thing is you need to find the bending moment in the general equation. You need to find the M at any section X, right? So you can cut a cross section here and try to have your x starting from here or x starting from here. For me, the best is x starting from here. This W I have here, the reaction is WL, and I have the bending moment, this is negative, and the bending moment is equal to WL squared over 2, right? That's the reactions that we have. So to find the bending moment X at any section X, you will take this cross section out here, something like this, and then the bending moment at section X is going to be equal to this piece is X and this is W. So you are going to have here MX is equal to
W.
the whole load is WX is affecting in the middle, so the resultant is equal to WX, this is R, and it's at distance X over 2, so the bending moment at this section,
WX squared.
WX squared over 2, that's the MX. Alright, so what is the double integration method is, like you guys remind me.
So we have the slope, it will be slope is equal to integration of.
Yeah, so you have d square y dx squared equal to m over ei, right?
Yeah.
So the thing is, we need to find this, and that's what we did here. So d squared y x squared, so we're gonna have 1 over ei multiplied by wx squared over 2. That's a very simple problem. So what is the problem with this one?
That's not a problem. The problem is the boundary conditions. So sometimes I have to include the boundary conditions.
The boundary conditions is, if you started the exit from here, so you are gonna put a boundary condition here, right? So this is at distance L, not distance equal to 0. You will say at x equal to L, what we have. This is x starting from 0 here. At x equal to L, y equal to 0, theta is equal to 0. I believe the boundary condition that you put, you said at x equals 0.
Wait, can you repeat that again, please?
Okay, so if I started x from here,
Okay.
so this is the boundary conditions, where the boundary condition is, at the fixation.
Yeah.
Y is equal to 0 and theta is equal to 0. There is no rotation and there is no deformation, right? Because this is the deformant shape. So I know that theta is equal to 0 and y is equal to 0. But if you exit from here, that's where you say at x equals 0, y is equal 0 and theta is equal 0. If you start the exit from here. But I started x from here.
Yeah.
But the thing is, it's also you can do that. But if you started the exit from here, like if I said, I'm gonna look not at this cross section, I'm gonna look at the other cross section. Look at what is our equation is gonna be. Mx is gonna be equal to WL multiplied by x. If x is starting from here, let's put it in a different color. So right now, the first one, I have x starting from here. If my x is starting from here, so when I come here, this is my x, all right? So I'm gonna have WL as a reaction multiplied by x. And then I'm gonna have this moment is negative. That's positive, that's negative. So this is gonna be WL squared over 2. And then I'm gonna have this distributed loads, which is W multiplied by x over 2, and it's a negative, so you're gonna have WX squared over 2. That is your moment equation. If you start from here, that's why I started from here, because it's a symbol, just one term. But the thing is, it's gonna make it a little bit complicated in the boundary condition. However, here, this equation is more complicated, but it's gonna make my boundary conditions as much simpler. All right, you got that? Okay. So I believe that's everything, and we are good to go to start a new topic. We're gonna take, as I said last time, we're gonna take a break from numerical methods and integration and math and geometry and all these stuff. So we are gonna spend around a month. So we are in September, so we have October, around a month learning SAP 2000, learning ETABS. We are gonna spend 1 week learning SAP 2000, or 1 week and a half, like 3 lectures. and maybe another 1 week learning ETABS, and 1 week learning tall buildings and seismic design and the structure analysis of tall buildings. And then we are going to have a little bit of practical analysis on a real tall buildings, which is going to be your project. And you were supposed to, we are going to have homework on SAP 2000 and also homework in ETABS, and I'm going to also give you the project information so that you can start when we start the ETABS part. You have a question?
Yeah, so then after the main term, we're going to start having classes on the second floor, or?
It's gonna be here. So you're asking if you are gonna work on computer with me or something?
Yeah.
No. So what I'm gonna do is I'm gonna record everything on my laptop. Like where I'm gonna do screen recording, and it's already recorded many times ago. And then I'm gonna upload it on YouTube. And then when you go home, you watch the video and you keep doing what I'm doing. So all what I'm doing, I'm just explaining how to do things, record them, and then when you go home, you try to watch the video and do the same example, the one that I'm doing. All right. As I said, you can use Citrix. You can write on Google FIU CEE Citrix, and then with your FIU account, with your Panther ID, you can access Citrix, and there's steps that you have to follow. I'm not sure. Do you guys have accessed Citrix before? Okay. So once you access, you will find SAP 2000 there. You can use that one. I tried this one before. It was very slow on my computer. Maybe on your computer it's gonna work great. So try this first. If you think it's a slow in solving the problem and take a lot of time, so you can download the trial version on your laptop, and you can use the 1 month trial version. We need SAP for like 3 weeks. So we're not gonna use SAP 2000 for the project. Okay, so you can try to do that. And that's what I'm doing. All right, and then we are gonna start ETABS. Does anybody have any questions for the project? As I said, we are like around 23 students in the class, so I'm thinking about groups from 3 to 4. Each group doesn't exceed 4 students. So try to pick your group, because after 3 weeks from now or 2 weeks from now, we are gonna start to work on the project. Okay. All right, so let's just start with, does anybody have any background using softwares, like structure analysis using SAP, ETABS, any software?
RAM
Raise your hand if you are. All right, what software did you guys use?
RAM concept.
RAM?
Yeah.
Okay, so do you use RAM for structure analysis or for post-tension concrete?
Post-tension.
Post-tension, because it's usually used for post-tension. Okay.
Yeah, RAM concept.
RAM?
RAM frame.
Cool. So you all use RAM? So it
Yeah.
sounds like it's a commercial. Okay, that's nice. So for post tension or for structure analysis in general? Post tension. But did you guys study pre-stress concrete before or no? So how you guys design post tension?
If it's red, it's failing. If it's
Oh, that's really great. Yeah, isn't that amazing? But it's better if you study the post-tension concept. You are gonna understand. I have, I believe, really good notes about that. Maybe I can share it with you guys if you want. But yeah, if it's good that you understand how's the post-tension work, how to calculate the forces. Manual. Yeah.
Would you consider teaching pre-stress concrete?
Well, I'm a structure analysis guy. I'm actually right now I'm a natural hazard guy. Like that's actually not my field. I'm structure analysis. But the thing is, any structure engineer or any, I believe, civil engineer has to have a background in structural engineering. So what I do actually for living is natural hazard modeling, like how hurricanes impacts buildings, how can we calculate buildings damage, how we can plan that communities can survive flooding, hurricanes, all this stuff. But to do this, you have to understand structure analysis, you have to understand natural hazard modeling, and I'm teaching class next semester about risk and reliability. Maybe another time we can talk about this. So that's what I do. Concrete is kind of like design guys, like guys in the concrete. But yeah, I mean, like I can teach it, but I have other things to teach. So, but anyway, so what I want to say is the concept of any structure analysis software is all the same. RAM, SAP 2000, ETABS. There is other software called SAFE to design slabs. There is software called Robot. Robot is like one of the software that Autodesk developed. I'm not sure if it's still out there or not, but I used it for a while. It's also another cool software if you guys use Revit to draw things. So basically Robot, that's what you do. You draw the whole structure on Revit, you just export the structure on Robot and do the analysis. You're not gonna draw anything. That's what I used to do. Once you have everything on Revit, export, run, export, put the loads, and actually calculate some loads for you. Calculates the dead load. All what you have to put is the live load, wind load, seismic load, and run the analysis, and everything is done. SAP 2000 is a very general software for any beginner who want to do structure analysis. Because it do almost everything. Like you put a tank, it's gonna do a tank. Shear wall, it's gonna do shear wall. Retaining wall, stairs, anything, you can do it in SAP 2000. However, there's some softwares are designed specifically to do analysis for specific components. Like ETAPS 2000, it can do many things, but it's a specialized in tall buildings. If you have multi-story building, 10-story, 100-story, 50-story, that's what is ETAPS is good at. Like this is how the interface of ETAPS is designed for tall buildings. You will find many tools that can help you. The thing is, there's an interesting tool in ETAPS that can help you in tall buildings, such that, like, let's say that you draw or you made a building of 50-story, and you forgot to draw a beam in 1 story, and it's already in the 50-story. There's an option that you can change. That I'm gonna make a change to this story, but make all these changes in all the 50 stories. So once you make this a change once, it's gonna change all the stories. So that's, I'm just giving you an idea how it's useful when you have multi-stories. So that's what ETAPS, when we have a tall building project, you are gonna see how we can, let's see. So we are gonna see how this is gonna help us. There's a software, it's called SAFE. Have you heard about that? SAFE is mainly to design slabs. You cannot have multi-story. It's only 1 floor, and that's what you can do. And also design foundation. If you have a pile foundation, footing, raft, so, and they all under the same company, Computer CSA or something like that. So, and actually it's kind of like, they could have merged all this in one software, but you know, like when you have 3 products like iPad, iMac, phone, so you can sell everything like twice or third, so they make more profits. I believe this is how the concept is, but it's really interesting tools. These tools do analysis, like you can put your structure there, and then you can run the structure and get internal forces. And once you get internal forces, you can ask the software to design the elements for you. Like once you pick the code that you want to design, you want the IPC, UPC, the European code. So you pick the code and run the design, and then it's going to tell you, oh, this element is going to fail or is not going to fail. This element needs this amount of reinforced concrete, amount of reinforcement or not. So that's how this software is doing. But the thing is, all the concept of all these softwares are the same. So let me tell you what are the steps of any software, solving structures using any software. First, you have to draw geometry. So any software, you have a plan, you have a structure, you have to draw the geometry. You have a truss, you have to put the geometry of the truss. There's many techniques to build the geometry in any software. Some softwares allows you to draw the geometry inside the software. And some softwares add other tools. Hey, you have your structures on AutoCAD, you can export the structure from AutoCAD to our software. You have your structure on Revit, you can import the geometry on Revit. So they save you a lot of steps. That's actually applied for SAP, ETAPS, Robot, and I believe RAM too, except exporting and importing from AutoCAD. So in the geometry step, you have to define boundary conditions. So once you import your structure, you have to tell the software, is this foundation fixed or hinged? Is this as roller, or is this is guided support, or this is a hinged support? So you have to define the boundary conditions. Okay, that's in the geometry step. Once you have the geometry of your structure is built inside the software, the second step is to assign loads. The thing is, if you draw the geometry of your structure and you run the structure and there's no loads, everything's gonna be 0. However, in SAP 2000, or I believe most of the software, when you run the software, you already draw geometry and you define that this geometry is a reinforced concrete. So he calculated the weight of the reinforced concrete and run the analysis based the elements that you gave to him, and you are gonna have some internal forces due to the own weight of the structure that you built. Unless you tell the software that the structure own weight is 0. Like, okay, let me tell you, like this problem. If I didn't give you W and you drew this on SAP 2000 and you run the model, once you run the model, it's gonna give you internal forces, even that you didn't define any weight. Because the thing is, once you draw this structure on SAP 2000, you have to say to SAP 2000, hey, the structure that I wrote, make the own weight is 0. And I'm gonna assign the weight by myself. I'm gonna put this weight, which is the own weight, by myself. Okay, so that's something that also we are gonna do. Yes.
So is there ever a time where you decided, is there ever a time where the self-weight is 0? Like where you want to...
In real life, no. But the thing is, I will tell you something that we do as engineers. Like, let's say we have a truss like this, and this truss hold a bridge or something. And I have this truss, okay? This truss hold a really heavy bridge slab here. This slab is like 100 ton or something. But the truss itself is very, very small members. Like every member is like 50 kilograms or something. So sometimes as engineers, we neglect the weight of the truss, and because the weight of the truss is very, very small compared to the weight of the slab. Because the thing is, if you consider the weight of the truss, like here at this joint and this joint, this is gonna be like a beam and it's gonna have a bending moment. In real life, it has a bending moment, but this bending moment is very, very small. Like this steel section is gonna take it and it's gonna absorb it and it's gonna resist it. Okay, so that's why sometimes, or most of the time, we neglect the own weight of the truss, unless if this truss element is really, really heavy, and we need to take it into account. So it's up to you. Like that's an engineering decision. So if you want to be accurate, yeah, you have to consider the own weight of the truss element, and try to see if this truss element is gonna fail this moment or not. Like with this section, if you bend it with its own weight, is it gonna fail or is it gonna pass? All right. But all the engineering problems, there's always own weight. If any member, like wood, it has an own weight. So anyway, so that's about the geometry. So we need to assign loads. And before assigning the loads, let's put two words here. Define loads and assign loads. Before I assign the loads, I have to tell the software, hey, I'm gonna, in 5 minutes, I'm gonna assign some loads. Some of these loads are dead loads, live load, snow load, rain load, seismic, wind. You have to tell the software before what kind of loads that you are gonna assign. So we do something called definition. We define the load. And we tell the software, is this load has an own weight or no? Like, I'm gonna assign this dead load and please exclude the own weight from the dead load because I'm gonna put it myself. If you want to let the software do the on weight part, yeah. Usually, when I define dead load, I leave the on weight inside the dead load. Okay, so it's up to you. You want to calculate the dead load by yourself, the on weight, and then assign it on the structure, or you want the software to do it for you. So that's what we do in the definition part. Once we define the loads, we assign it on the structure. Okay, so that's a step number 2. Step number 3. Is we run the analysis. Once we assign the loads, you have to check if you have an intermediate hinge, if you want to release something. We are going to learn all that, but this is considered part of the geometry. Then we are going to run the analysis, and then number 4, we need to visualize the results. That is the main steps of the analysis using any software. Does anybody have any questions? Structure analysis. All right, so before I start SAP 2000, I want to introduce you what elements that we use to model structures. So we have 4 elements. So I have 4 elements. I have something called frame element. I have something called plate. I have something called membrane. I have something called shell element. So let me write the names. Frame, plate, membrane, shell. By the way, this is really, really important concept. I know that you guys sometimes use software, but you don't know what elements are you guys using. If you want to be a pro in what you are doing, you have to know everything about the elements that you are drawing. And I believe the interviews in big companies, they ask about these things like, hey, I have a shear wall. Do you think I use a membrane or a plate or a shell element to model them in software analysis like SAP 2000 or something? So you have to understand what each one of these ones is doing. There's a solid element, maybe we can talk about it if we have time. Yeah.
The plate and the shell, let's see, is it has a baseball? The plate and the shell, like they look like they're the same shape.
Oh yeah. Actually, I can draw this the same shape. It's just like I'm drawing them that way so I can visualize something. But they are all plates. Like this can be plate, like this slab can be plate, can be shell, can be something else. All right? Okay. So for the frame element, I have at each node 6 degrees of freedom. We use the frame element to model beams, to model columns, to model any linear element. Okay? Any beam, any column, any small element that has 2 dimensions smaller than the longest dimension, you can use frame element. The degrees of freedom is something like this. You have 1, you have 2, and you have 3. 1, 2, 3. Same thing here. 1, 2, 3. Has 6 degrees of freedom at each node. Sorry, let's put them one by one. 6 degrees of freedom, 3 translation and 3 rotation. So I have 1, 2, 3, and I have rotation here, and rotation here. That makes them 6. So 1, 2, 3, 4, 5, 6. Same thing here. 1, 2, 3, 4, 5, 6. So imagine that's my frame element. It's something like this. Alright? In the structural system, each point can move X, can move Y, can move Z. So X, Y, and Z can move X, Y, and Z. And can rotate about X, can rotate about Y, can rotate about Z. So it can have 3 rotations. Same thing here. Alright? So if you put a hinge here, you are gonna restrain the 3 translation. Like if I put a hinge here, I'm gonna restrain translation 1, 2, 3, but the rotations can rotate around any point. But if you put fixation, you restrain the 6 degrees of freedom. Because right now we are 3D, not 2D. Because structure analysis is 3D. All right. So how about plate? Plate is something like this. All right. This thing. Let me put these here. Right, imagine this is a slab, like the one that we are on right now. This is a plate. The plate can rotate that way, like each joint can rotate that way or can rotate that way. So that's a plate. It bend this way and bend this way, 2 ways, okay? And it can be formed downward, but it cannot move X and cannot move Y, and cannot have a torsion that way. So this slab that we are in can bend this way because of our load. Once we put the load this way, it's gonna bend that way. And it's a two-way slab, so it's gonna have two-way moment. And there's a deformation in the middle. There's like 1 centimeter or 2 centimeter deformation, but we cannot feel it. So it can move downward, but we cannot. It cannot move that way or cannot move that way, and it cannot rotate. It cannot have torsion, right? That's the plate. How about the membrane? The membrane is something like a shear wall. The shear wall, look at this, shear wall, it doesn't bend that way, but it bended that way, because it takes most of the load in this direction, so the bending moment is that way, so it takes torsion in plane moment, and every point can have X and Y deformation, all right? X, it can move X, and it can move Y, right? But it cannot move Z. That's the membrane. The shell has the advantage of plate and membrane. Each point has 3 rotation and 3 translation. So basically, you can forget about the plate and membrane, and any plane element you can assign a shell. Is this a plate or a membrane? And you will think about a lot. No, I'm gonna assign a shell element. Because sometimes, let's say that you have a retaining wall. Do you guys know what a retaining wall is? You have a soil behind. So the soil makes this bend that way like a slab. And maybe you have a seismic, you can have in-plane motion. So it has plate loads and membrane loads, or plate deformation and membrane deformation. So you need to assign shell to this. Same thing like swimming pool. Swimming pool has water here and soil here. So it can have bending moment like this. And if there's a seismic happen, this wall is gonna have a bending like this. All right? So shell can have the advantage of both members. Why I'm saying that? Because the thing is, once you start defining a member, the SAP 2000 is gonna ask you, is that a frame? And actually, the frames are isolated in a separate section. But the thing is, the most complicated part is the slab. Tell me please, is the slab a plate or a membrane or a shell? I always, all the time, use shell. I don't think, because I use the shell to draw the shear walls and draw the slab. Okay? But if you want to go old school, any slab, it's a plate. Any shear wall is going to be membrane. So if you have an interview and he asks you, you have the option between 2 things in a structure analysis software, between plate and membrane, and you want to model a shear wall. Which one are you going to use? You're going to use a membrane. Okay? Somebody have, yeah.
You said it was a grid slab, right? So it can bend that way and this one that way. Is that the standard, or because if you do
No, if you have one-way slab, same thing.
Okay.
The other moment is gonna be 0.
Okay.
The other deformation is gonna be 0, but you can. So it's used to model slab systems. And in the foundation, it's a plate too. If you have a raft foundation, do you guys know the raft foundation? Raft foundation is. Okay, let's talk 5 minutes about foundation. When we have a structure, we need to have foundation. The foundation can be different types. It can be isolated footing, you can make a square and the column is coming onto the square. And sometimes when two footings are very close to each other, we combine, it's called combined footing. You combine 2 columns together. But what if 5 or 6 or all the columns footings are intersecting with each other? We make a whole big slab. Take all the columns at once. If I have, let's say, foundation. Can you shift the camera a little bit? Foundation. All right, so if I have single column, I can make something like this, footing. And we designed the footing to take this load. So what if I have a column very close to this one, and I assume that first it can be isolated footing, but when I designed the foundation, I found that the load is very, very big, and this foundation needs to get bigger, and when I got the foundation bigger, it intersects with this one. So we combine them together. We make a combined footing, so that's another one. So you have either, you guys didn't take a foundation class before? Okay, so I have footing. Oh, sorry, it's called isolated footing, and here it's called combined footing, And the thing is, if you have multiple columns, like let's say that you have 10 or all the columns in the structure are intersecting with each other, so you make a raft foundation. Like you have something like this, and this is basically, you come to the site and you will find reinforcement all over the place, here and here, and there's a lot of stuff. And then you get all the trucks and keep pouring concrete, so you will find a big slab on the whole area, and this is called raft foundation.
Is it also called mat foundation or?
Or mat foundation.
Oh, okay.
Yeah, same thing. Raft foundation or mat foundation. Alright, what if after I put this and still the soil cannot take it? If I use raft foundation, so this is how I escalate my foundation. From footing to combine and then raft foundation. Sometimes after I put raft foundation, still the soil is gonna fail with all the loads that I have. We put piles. We take all the load from here and we put piles like this here, and maybe some here, and some here. Sometimes the soil here is not good enough to take all the loads. The bearing capacity of the soil is not good. So we take the load, and the load basically is get distributed into friction on the pile, something like this. Like basically, the load is coming from here like this, so the pile is gonna have some friction, like this, and then the tip here, there is a reaction here. So the load that comes from the structure is getting distributed on the side of the pile and at the tip of the pile, at the base of the pile, something like this. So that's how we design piles and how we can find, basically if I have 100 ton and the friction of one pile, let's say it can take 5 ton and the tip can take 5 ton reaction. So basically one pile you have only can resist 10 ton. So how many piles do I need so it can resist the 10 ton? 10. So I need 10 piles to resist this one. Okay, so that's how we calculate the number of piles that we need. And sometimes you don't do the raft foundation and you put piles under and that's what we do mostly in bridges. You have one column from the bridge, you put some pile, and you take the load. So yeah, we model the raft as a plate. We call it thick plate because usually the raft foundation is 1 meter, 2 meters, sometimes 3, sometimes really big. So if you want to use shell, you can use shell as well. Okay, let's see the degrees of freedom that I have in the plate. The plate doesn't have X and Y, but it has moment around X and moment around Y, and it have one vertical degrees of freedom. Same thing here, you have a moment here about X and about Y, and you have degree of freedom up. And this one, and one up like this. So I have here 12 degrees of freedom. Here I have also 12, because I have 3 and 3, 6. The membrane has the opposite degrees of freedom that you have here. It has an X, and it has Y, and it has a moment around Z. So it has moment inside this one. Because the thing is, if you have a shear wall and the load is hitting that way, so the shear wall, if you have the load that way, is going to bend that way. So the degrees of freedom is equal to 12. The shell has all of these. It has X, Y, Z, and moment around each one of these. So each one of these has 6 degrees of freedom, so the total number of degrees of freedom is 24. That is the elements that you have for the structure analysis using software. Does anybody have any questions so far? All right, so something else before we start doing any examples on the computer is the local coordinate system. Let's say global and local coordinate system. Any software has a global and local coordinate system. Global coordinate system is 0, 0, 0, the XY coordinate. Like there's a point that is called origin, and this origin has X and has Y. So this is Z, and Y is something like this. This is Y, and this is Z. I don't know, whatever. So X, Y, and Z is going up, right? You guys imagine the plane. This is very confusing, right?
No,
It
it's
doesn't
okay.
make any sense.
It's good, it's good.
Well, okay. This, and this, and this.
Perfect.
Alright. So that's the plane. The thing is, each element that you draw inside the software has a local coordinate system. Like let's say at some point this is 0, 0, 0, and you came at a random point in the screen and you draw a bar, an element. This element is gonna generate a local coordinate system. What is the local coordinate system? Let's see the colors, because it has some colors. So you are gonna have X and Y and Z in U. It's called local coordinate system. But it doesn't, it's not X and Y and Z. They call it 1, 2, and 3. Okay? So you are gonna have a red arrow, something like this, and it's gonna be, this is coordinate system number 1. And then you are gonna have a blue arrow, something like this. This is number 2, like X and Y. And then you are gonna have a green arrow, that's number 3. So that's 1, 2, and 3. And that's really, really important. Why? Because the thing is, when you are gonna show the internal forces inside this element, is gonna be with respect to these forces. Why it's important? Like let's say you are gonna show the normal force. The normal force is gonna be in the direction of 1 or 2 or 3. 1. Why? Because 1 in the direction of the member. So normal force is 1. So what if you are gonna show shear Q number 2? What does that mean? Q2 and Q3. Q2 means, like, if this is your cross section, look at this. That means shear is going that way. Q3, that means shear that goes this way. So that's why you have to know what is 1, what is 2, what is 3. Most of the time, our load is going down. It's not going like, my beam is like this and my load is like this. So all our shear is Q3. You only have Q2 if your load is like this. You're gonna end up with Q in direction number 2. Because if our load is going down in the direction of local axis 3, so we usually show Q3. However, when it comes to bending moment, we show bending moment around 2, because that is 2, and my cross section has bending moment around 2. So most of the time we are showing M2 and Q3. You will tell me, so there's no way that I'm gonna get M3 and Q2 and M3. There is a way that you get M2 and Q3 if you have your loads in plane like this. You're gonna have shear in two direction, in direction number 2, like this, and your moment is gonna be around 3. Okay? Alright. So that is about the local axes. Let's put the local axes for the plates or the shells or the membrane. So if you have, I'm gonna put it here. Let's say my shell is something like this. So the local axes, you're gonna have 1, it's usually in the X direction, and then you're gonna have the blue is in the Y direction, sorry, the green, it's going up, blue, and then you're gonna have, because I don't have green, I have green actually. I'm gonna have this then. Number 2. All right. So that's the shell or the membrane system. You're gonna have, actually they are colored in ETAP something like this. Yeah.
Isn't the other one the green?
This one is green.
Yeah,
3.
2.
Oh, sorry, 3. 1 is red, 2 is green, 3 is blue in the shell. 1 is the X direction of the shell, 2 is the Y direction of the shell, 3 is the Z direction of the shell. So if you want to show the bending moment M11, so that's basically the X direction. M22, that's the Y direction. If you want to show the deformation, it's the deformation in the direction of the 3 axes. That's why you have to understand the local axes of any structure before you do any analysis. Because if you don't understand the local axes, you will not be able to show results. Because to show results, you have to understand what is 2, what is 3. Because my shear is in the 3 direction, and my moment is about 2 direction. All right?
Why do they change the colors?
I don't know. That's what they do. All right. So each software has its own stuff. You know. Maybe they change it because this is based on old stuff. So we're gonna find out. The thing is, okay. Let's talk right now. We talked about geometry. All what we have been right now talking about is geometry, and I'm helping you right now to understand the different element that you use to draw your geometry and the local axes of your element. Okay. So what I'm going to do right now is to introduce you to the loads. Let's talk more about loads. So for loads, the thing is, if you are drawing a real structure, like you are a structural engineer in a structural engineering firm, and you are going to design a building, I usually have the own weight inside the dead load, and I don't touch it. And I let the software calculate the dead load for me. And I make the dead load factor equal to 1. Like, oh, I ask the software, hey, I'm making a load case. This load case is called dead load. And calculate the own weight of the structure based on the density of the material that I gave to you, and assign this own weight in the dead load. Okay? And I make another dead load, it's called super dead load. This super dead load has the flooring, and I calculate the flooring by myself because every structure is different. Some structures, they are gonna have wood flooring, a tile flooring, marble flooring. Everyone has different weight. So I make a load case, it's called super dead, and I calculate this load and I assign it inside this load case. Okay? So right now we know dead, super dead. There is a load case that's called live load. Each structure based on its use has different live loads. Like residential building is different than commercial building, is different than universities because there's lots of people in this room. So the live load definitely is much better. That counts for our load, the chairs, the furniture, whatever that happens here. And we calculate based on the maximum, like this room is really full. Okay? There's what do you guys think the biggest live load in a structure that can happen? Any structure that you think it has a huge live load? Stadium. That's really good ones because sometimes it gets full. What else?
The trucks.
The trucks?
Yeah,
I'm thinking about a structure, not the live load itself. Yeah, the trucks is really huge live load on the bridge. But we are talking about a structure that has a huge live load, libraries. Yeah.
A mechanical room?
A mechanic room?
Yeah, like they.
That's an equipment. So it can be counted as a live load, but we account for vibrations as well. But yeah, it can have a huge live load. But what I want to say is libraries has a huge live load because of the books.
Oh,
The books
library.
is really heavy. And I believe if you look on the AC 722, whatever version out there, you are gonna find out that the libraries has one of the massive live load. Definitely also the garages also has a huge live load. So live load is really sometimes gets really huge. Also there is a snow load that happens on the roof of the buildings. There is a rain load. There is a wind load. There is a seismic load. There is a lots of loads. There's a special structure that has loads that you have to account for special types of loads. Okay. All right, so the thing is, all these loads come together on the structure. Like this is structure right now, it's under its own weight, under our live load, and maybe under other loads that can happen randomly, seismic, wind. But the thing is, what is the chances that this structure is going to have the maximum of all these loads one at a time? There's no chance. Maybe there is, but it's low chance. That's why the engineers or the researchers did some statistics so that they can come up with the extreme loads events for the structure. They make something called load combinations. They say, hey, but the thing is, when they did that, like they did some statistics and they found out that the maximum seismic cannot happen with the maximum wind. Because there is no way, yeah, you can have a seismic and wind at the same time, but not the maximum seismic that can happen in the whole lifetime of the structure. that can happen, I mean like seismic and wind together. So they made something is called load combinations. So if you went to chapter 2 in the ESC 722, you will find some of these load combination is, they said that the first load combination that you need to design your structure for, it is 1.4 dead loads. Like you will say that this structure doesn't have any live load, and you are gonna assume it has 1.4 dead load. And the second load combination is 1.2 dead load plus 1.6 live load plus 0.5 any roof load. This roof load can include live load on the roof plus, or like here in Florida, we don't design for snow. This can be snow load, but we definitely can design for rain. Okay, you try roof live load. What is the roof live load? Because the roof is a little bit special because it has insulation, it has sound resistance, it has equipment, whatever the structure that you are designing for. So sometimes they have a special roof live load. We calculate the live load of the structure separate from the roof live load. Because this live load can be mechanical, can be snow, can be rain, can be multiple things. All right? Number 3, 1.2 dead load plus 1.6 plus 0.5 live load or 0.5 wind load. Anyway, there's multiple of them. I'm not gonna write all of them. Like let's say 4, 5. You can check the standards and you are gonna find all of them. What I'm gonna use in this class, I'm gonna use only dead and live, just for example. But you know, when you design for real structures, and also in the tall building design, we're gonna design for wind and seismic. Okay? But in real structures, you have to follow specific load combinations when you design the structure elements. Okay? So that's for the loads. I want also to talk about something else. When we draw the geometry, actually it's before drawing the geometry, so let's put it this before that. You can actually do this step after you draw the geometry, but it's better to do it before. It is called define the material. Define material. I mean, if it's 2, 3, 4, and 5. I would rather define the material before I do anything. You can actually define the material after. Like you can complete the whole structure and then you can assign the material. But I would rather define this before, because once you define the material, like let's say that you define concrete and you define steel. Before you draw any geometry, the software is asking you, is this concrete or steel? So it's like an embedded step that saves you all the steps downstream when you do the analysis. So when you draw, basically when you draw the geometry, you draw the geometry and define the material and assign the material as well. So you don't have to spend more time at the end of your design process to assign materials. So let's talk a little bit about materials. So I'm gonna talk about steel and concrete, and mostly concrete. So, but before I do this, I just wanna make sure that you guys understand the unit conversion. Do you guys know what is 1 megapascal? Okay, what is the pascal? It's Newton per meter squared, right? So, if I wanna convert this to Newton per millimeter square, can you convert it? So what should I do?
It should be
Multiply by
times 1 meter squared over
1000. 10,000 square.
Yeah, so I'm gonna do 10 to the power 6, and if I put the Pascal here, so this is gonna be Newton per millimeter square, right? So I divide this by 10 to the power 6. So 1 megapascal is 1 multiplied by 10 to the power 6 Pascal, right? So 1 megapascal is equal to 1 multiplied by 10 to the power 6 multiplied by, like, if I divided this by,
It's 1 Newton per millimeter square.
yeah, so this is exactly, so this is gonna be equal to 1 Newton per millimeter square. Because the 1 megapascal is 1 million Pascal. And 1 million Pascal is equal to 1 Newton per millimeter square. You guys got that? It's just a simple conversion. So how do you convert actually? Like, let's say this is the Pascal is Newton meter square, right? So if you want to convert this to millimeter square, so actually the meter has 10 to the power 3 millimeter, and all this is a square. So basically this is equal to Newton 10 to the power 6 millimeter square. So you divide the unit up and down, and then you try to convert each one separately. Okay, so that's something that I needed to make sure that you guys understand. Okay, so let's talk about number one, the concrete. For the concrete, the youngest models of the concrete were the American code is equal to 4,700, the square root of the characteristic compressive strength of the concrete. So if you have the characteristic compressive strength of the concrete, you take the square root of this value, multiply it by 4,700, it's gonna give you the youngest modulus of the concrete in the megapascal. Do you know what is the characteristic strength of the concrete? You take some samples from the concrete that you are using in the site, and you do the compressive test, and you take the average, and the average is gonna give you after 28 days, and you get this value. So basically, some material left. Thanks. Usually, for each project, you have the FC.
Do they drill cores in the slab after it's been poured, or do they grab it when it's still like?
Before. The thing is, they have like each truck, when it goes to the site, they have to take some cubes from it, and they go test it. If it failed the test, everything it has like the one
break
yeah,
it and rebuild.
Exactly. From every truck. That's actually the standard test. So same thing, the E-concrete, if you want it in a different unit, is equal to 57,000, the square root of the compressive strength, and here is gonna be in pound per square inch, PSI. Okay? All right, so there's something called the Poisson ratio of the concrete, and it's equal to 0.2. The Poisson ratio is the ratio between the longitudinal strain to the lateral strain. Like if you have, this is your concrete, and you try to compress, so this way is the longitudinal, and this is the lateral one. So you will divide this over this. Okay, so that is the ratio between them. That's the Poisson ratio of the concrete. The gamma, the density of the concrete is 2.4 ton per meter cube. So this is mostly the parameter that we define when we use material. Yeah.
So we're going to ask us if the concrete has if it's a lightweight or a normal weight.
That's a really good question. If it's lightweight, so the density is going to be different. So if you have multiple concrete in the site, and actually that happens in tall buildings, but not lightweight. Maybe you have lightweight. You use, the thing is, when you have a tall buildings, the loads on the columns are huge, because it takes loads like the column down, like in a story, like let's say in a versus story, and the building is holding 50 story. So can you imagine one column is holding 50 story? That's a huge amount of load on one column. So we usually use a high strength concrete or ultra high strength concrete. The ultra high strength concrete, FC, usually is around 30 megapascal. But in columns, we use 60 and sometimes 100. We use concrete strengthened by fiber, very, very special concrete. So this number can be changed if you have a special concrete. But in our project, we're gonna use the same concrete. Maybe, you know what, maybe we are gonna use high strength concrete or something. So you have to define two types of concrete, okay? But for the slab system, you don't need high strength concrete. You need regular strength concrete and maybe lightweight concrete. You know why? Because it helps us reducing the loads on the column. Rather than having a density 2.4, I'm gonna have density 2 or density 1.5. If you reduce the load of the slab, by the way, the slab is the main load on the whole structure. Like the columns itself, weight is 10% of the structural load. The slab is 90% of the structural load. If you were able to reduce their loads, you are gonna reduce the load on the columns and reduce the cross section of the column and then save money. Okay? All right, but lightweight concrete is not a cheap tool, right? So you have to do some economic cost analysis. All right, so that's the regular concrete material characteristic. So let's say that sometimes we say I have concrete 30, that means that the compressive strength of the concrete is 30 megapascal or 30 Newton per millimeter square. So if you want to convert this to ton per meter square, like let's say I want to convert this ton per meter square, so I do it step by step. 30, I'm gonna multiply. I have to convert Newton to ton. So if I want to convert Newton to ton, let's convert Newton to kilogram. What is the conversion?
You said Newton like a kilogram over
1 over 9.81, right?
Yeah.
So that's to kilogram. If you want to convert the kilogram to ton, so you still have the 1 over 9.81 and 1 over 1,000 because the kilogram is 1 over 1,000 of the ton. So to convert 30 Newton from ton, so you have up 9.81 multiplied by 1,000. That is ton. I want to convert it to ton per meter square. You have to convert the millimeter square to meter square. The millimeter is 10 to the power 3, but the thing is it's a square. Sorry, it's a square. So it's gonna be 1 mil. So this is how we do the conversion, and it's really, really important. You convert the top unit and the bottom unit. So here I converted the Newton into ton and the millimeter square to meter square. So this is right now is ton, and this is right now is meter square.
You don't use PSI and KSI?
You have to find a conversion from Newton to pound and from millimeter to inches. It's gonna be huge, but it's doable.
But I mean, when you do your analysis, you use a lot of.
And in the US, it's mostly, but if you do something international, you use the metric units.
Okay, but usually here you
It's
use
the pound
mostly-
per square inch, yeah. Right, so this is gonna be equal to 3058 ton per meter square. All right, so that's for the concrete. So let's go to the steel. Number 2. Steel, the youngest modulus of the steel is around 200,000 megapascal.
That's
And the youngest modulus of the steel is a little bit bigger, the Poisson ratio. And the gamma of the steel is 7.85 ton per meter cube. All right, so I believe that's very, very important introduction to the analysis of structure using software, because if you know these basics, so you are just like a robot, like you're just somebody's telling you things and you're putting in and you're getting out. But here you understand what is every component characteristic is, the shell, the blade, the membrane, what is the global and local axes, what is the materials, where it comes from, because sometimes there's a special project that you get, like tall building or something. In tall buildings, I remember once in the firm, like when I was in Egypt, we were designing a tall building, we had multiple types of concrete for multiple sections. So, because the thing is, when you have a tall building, it is not the building that you design and we are done. We do value engineering, we do economic analysis, we have to reduce the amount of reinforcement, we have to reduce many things, because if you reduce something in one story and you save, I don't know, $100,000 in one story, you have 50 story, you save $500,000. So it's really important that we like understand the different components that we have when we do structure analysis using software, but mainly any software, it is the system. You define the material, You draw the geometry, define and assign the loads, run the analysis, and then visualize the results. So with this, I believe we are good to go next time, I mean like next week, and we do our first example on SAP 2000, right? Try not to install the software right now, wait until next week so that you don't use the 1 month trial, so we need to be efficient, okay?
When we're here, we use.
If you want to bring your laptop and do with me, that's fine. Like if you want to bring your laptop and follow me, that's fine. If not, you can watch the video and do it when you go home. Okay? Right, see you.